The comparison test and the limit comparison test are two tests we can use to check whether a series converges or diverges by comparing it to a known series, usually a p-series or a geometric series because they're the easiest to work with. The direct comparison test is as follows. Suppose that you have a series, the sum of an, n starts at wherever it starts, and the sum of bn. Suppose these are two series with positive terms. Very important that we are working with series with strictly positive terms. Otherwise, these tests do not work. The first part says if your series, the sum of bn, converges, and every an is less than or equal to every bn for every value of n, then the series an converges. In other words, the series an converges because every term in that series is less than the term of a similar convergent series. And if the sum of bn diverges, and every an is greater than or equal to every bn for all n, then the sum of an also diverges. Again, each term is greater than the corresponding term of a divergent series, so it must diverge. Let's look at some examples. Let's figure out if this series converges or diverges. The sum as n goes from 0 to infinity of 5 times 2 to the 2n plus 1 over 3n minus 1. This series is not any of our common known types of series like a p-series or a geometric series, but it does have some resemblance to a geometric series. Because you see we have a 2 to a power in there that involves an n on the top and a 3 to the n on the bottom. So perhaps we might want to compare this to a geometric series. Let's pull out the function that describes our an's here. So an is 5 times 2 to the power of 2n plus 1 over 3 to the n minus n. Now let's try and manipulate this a little bit and see what we can do with it. So first things first, I don't like that I've got this weird 2n plus 1 in my exponent on the top. I'd like to adjust that a little bit. So this is the same thing as 5 times 2 times 2 to the 2n power. And on the bottom we've got 3 to the n minus n. So I can rewrite that. That's actually going to be 10 times 2 to the 2n. But actually, 2 to the power of 2n is the same thing as 4 to the n power, right? 2 to the 2 is 4, and then take that to the n power, that's 4 to the n, over 3 to the n power minus n. Now you can see a little more clearly the connection here between this series, the terms of this series, and the terms of a geometric series. If we ignore that 10 on the top and the minus n on the bottom, then you could look at this expression here and say, well, 4 to the n over 3 to the n, that's 4/3 to the n power. Now that would give us a geometric series, but it would give us a geometric series where the r is 4/3, which is more than 1, which means that series diverges. So let's try and compare our series to the series where the terms are 4/3 to the n power. So let's compare to 4/3 to the n power, the terms of that series. If we stick a sigma in front of this, well, we know that this series diverges. So what can we do? Well, I'm actually going to leave that 10 in front of this as well. Let's put the 10 right here, because this is still going to give us a geometric series that still diverges. So having a 10 as a multiple is not a problem. What about that minus n in the denominator? Well, what happens if I just look at 10 times 4 to the n over 3 to the n? That is equal to 10 times 4/3 to the n. Which of these two is bigger? Well, the first one has a smaller denominator. As long as n is positive, 3 to the n minus n is always going to be less than 3 to the n. So the second part has a larger denominator. So which of these two expressions is bigger? Well, the one that has a smaller denominator must be a larger fraction. So I can say that this first part here is greater than the second part. So let's just summarize this here. Let's let Bn equal 10 times 4/3 to the n power. So what do we know? We know that, first of all, the sum, as n goes from 0, I'll start at 0 this time as with before, of 10 times 4/3 to the n, that series diverges because it's a geometric series with our r equal to 4/3, which is greater than 1. And second fact we know is that our an, which is 5 times 2 to the 2n plus 1 over 3 to the n minus n, is greater than, and therefore greater than or equal to, 10 times 4/3 to the n, which is our Bn. So these two facts tell us, by the direct comparison test, that our series diverges. So the sum of an diverges. And that is our conclusion. Let's take another example. Listen to the series, the sum as n goes from 1 to infinity of n squared plus n over 3n to the 4th plus 4. So the thing to do here is to ask yourself, usually we're going to want to compare our given series to a series that's either a p-series or a geometric series. You might use a different series if you can identify a different series that you know whether it converges or diverges. But typically the ones that are easy to work with are either p-series or geometric series. Now the function that describes our an's here is n squared plus n over 3n to the 4th plus 4. Now this is entirely an algebraic function. There's no variables in any exponents here. This is an algebraic function. And algebraic functions are going to tend to be best compared to a p-series. But which p-series? But let's see what we can do. So I'm not sure yet if I think that this series is going to converge or diverge. If I suspect that this series converges, I'll need to compare it to a series where this one has terms that are less than another series. If I suspect that this series diverges, I'll want to compare it to a series where this series has terms that are greater than the other series. I don't know yet, so let's just play around. Here's the first thing I'm thinking here is that plus 4 in the denominator, kind of like in the last example, I'd like to get rid of that plus 4 and ask myself, how does that compare to a new expression here? So n squared plus n over 3n to the 4th power. So which one of these is bigger? Well, 3n to the 4th plus 4 is greater than 3n to the 4th. So the first expression has a bigger denominator, and therefore the first expression is smaller overall. It is less than or equal to, in fact strictly less than, n squared plus n over 3n to the 4th. So at this point, I've got a convenient expression that I know is greater than the series I'm interested in, which means my series, my an's, are less than something else. So maybe I'd like to try and figure out a p-series or some other series that I know that my an's are less than, and which means that maybe I'm suspecting that my series converges. How can I prove that? Well, the trouble is that, I'd like to say that this is less than or equal to something else. And what I'd really like to do is get rid of that plus n on the top. I'd like to have an n squared over 3n to the 4th, because that I can deal with. That is actually very, very close already to giving us a p-series, and that's not a problem at all. Then I'll really understand. The trouble is that n squared plus n is not less than or equal to n squared. it is in fact greater than or equal to n squared. So I cannot write the expression that I've got here. This is not true. Here's what I can do, however. I can throw in a coefficient on the top if I want to. It is true that this is less than or equal to 2n squared over 3n to the fourth. Why is that? Well, n is always going to be less than n squared as long as n is large, right? If n is very small, say less than 1, then n squared is less than n. But we're talking about values of n that are 1 or higher, so n is always less than n squared. So taking n squared plus n squared is certainly bigger than n squared plus n, which means that 2n squared is bigger than n squared plus n. So that tells us that n squared plus n over 3n to the fourth is less than or equal to 2n squared over 3n to the fourth. And this equals 2/3 times 1 over n squared. So let's let our bn equal 2/3 times 1 over n squared. And we know that, first of all, that an is, in fact, less than or equal to bn. We've just proved that. Here's our an here, and here is our bn here. And we've just determined that our an is less than or equal to our bn for all values of n. Very important you check this for all n, not just some random values of n. Of course, if n were less than 1, we could not say this, but we are specifically starting with n equal to 1, so we're good. Next question, what about the series, the sum of bn? Well, take the sum as n goes from 1 to infinity of 2/3 times 1 over n squared. We can factor out a constant multiple. Remember, this is an infinite sum, and we can factor constant multiples out of a finite sum and also out of an infinite sum. So this is equal to 2/3 times the sum, as n goes from 1 to infinity, of 1 over n squared. This is a p-series with p equal to 2, which is greater than 1. And we know from our theorem that a p-series in which the p is greater than 1 converges. So, our sum of bn converges, and our an's are always less than our bn's for every value of n. So the series we're actually interested in, the sum of an, also converges. Let's talk about our general strategy for using the direct comparison test. The strategy is, given a series, sum, n starts at wherever you want, up to infinity, of an, that you're interested in testing. First of all an's must be positive. That is a requirement for this test. So, given that that's the case, two things you can try. One thing is, if you suspect you already know that your series either converges or diverges, then pick a series you are familiar with that you know whether it converges or diverges and try that. More often what you'll do is you'll want to kind of manipulate the expression for an and see if you can find a simpler expression and determine whether your an is greater than that expression or less than that expression. And eventually you will get a new expression bn, which gives you a series that you are familiar with whether it converges or diverges. So, then you'll just check. If your series bn converges, then make sure that your an's are always less than your bn's, or equal to, and you'll know that your an series also converges. And if your sum of bn series diverges, then you'll check and make sure that your an's are always greater than or equal to your bn's, and you can conclude that your sum of an series diverges. Sometimes, like in the last example, you'll need to let your new series that you're comparing to be a multiple of some familiar series. So a multiple of a geometric series is technically still a geometric series. A multiple of a p-series is not strictly a p-series, but it will certainly have the same convergence or divergence as the p-series, and it's a multiple of. So that's often the case.